All right, welcome back. I want to kind of make a quick video here about how to use the comparison test and things we might look for. So again, we're going to tread lightly about this for now with our integrals, but we're going to come back to it a little bit more focused when we talk about sequences and series. And so there's a web work question that's kind of similar to some of this. And let's imagine we had to figure out whether this integral, e to the minus x squared over x squared, converged or not. Now, we could try to evaluate it using substitution or integration by parts. Both of those would be pretty challenging. I'm not sure either of those would work. But if I look at it, let me do this in a different color. What color would be good? Maybe red. So if I look at this, I say that the numerator seems really small. And I look at that, e to the minus x squared, that's really tiny if x is big. And so that intuition makes me think that maybe e to the minus x squared over x squared, maybe it's true that this is going to be smaller than 1 over x squared. And I think about it and I say, oh yeah, e to the minus x squared, as long as x is bigger than 1, this is going to be like 1 over e or 1 over e squared, or basically 1 over a really large number. And so I might choose this as my comparison. And if I just sort of think through what's true, well, if I take the integral of 1 over x squared on the same range from 1 to infinity, that's going to be convergent. So this is going to be convergent, and so the integral test by comparing to 1 over x squared is going to make me think that the answer to this question might be convergent. And so again, what I did was I kind of looked at it and said, oh, why don't I just compare to 1 over x squared since my denominator is so small? So let's move on to the next one. So now I've got x over x to the 8 plus 17. Now x itself isn't so small. So if I look at the numerator, x is probably a million, or could be a million or a billion. It can be any number really between 1 and infinity. So I can't use the same sort of trick. But what I can do is I can say, well, look at that denominator. That square root of x to the 8 plus 17, that's going to be a larger denominator than just taking the square root of x to the 8th. So think about that. That denominator where we add 17, that's a lot smaller than not adding 17. And so we have this sort of expression there. And if I simplify this, if I just kind of simplify this here, if I have an 8 plus 17, that's going to be smaller than x over the square root of x to the 8th is x to the 4th, and that's going to simplify down to 1 over x cubed. And so what I've done is I can compare my series with 1 over x cubed. And 1 over x cubed is a much simpler integral. And so if I can tell whether or not the integral of 1 over x cubed from 1 to infinity, whether or not that is convergent or divergent, I'll know information about our original problem. And so maybe I'll leave that one as a question for you, is what is the integral from 1 to infinity of 1 over x cubed dx? Is it going to be convergent or is it going to be divergent? That's just something to think about. And great. So let's move on. I'm gonna clear this up just a little bit. So in our next problem, we have cosine squared over x squared plus 9. And I look at that, and I look at this cosine squared, and I say, well, this has to be between 0 and 1, basically. So I've kind of drawn that little thing there, because if I take cosine, it can be between 1 and negative 1. But when I square it, it has to become positive. So I've got this thing, and it's kind of bound between 0 and 1. So I might actually say, oh, that probably means that this fraction, well, it's probably smaller than 1 over x squared plus 9. And in fact, why don't I just get rid of the 9 at the same time? So let's think about that. Let's compare these two fractions. This has a smaller denominator, and it also has, sorry, I meant smaller numerator. So it's a smaller numerator, and it has a larger denominator. And so to me, that means that this fraction on the left is definitely going to be smaller than the fraction on the right. And so we would then use 1 over x squared in our comparison test, which is going to help us out. Okay. So, and that's quite good, because I think we've already seen that the integral of 1 over x squared is going to be convergent. That's really great. Finally, we've got this integral here, and I look at it and I say, well, that's 17. Seems a little, it's not super small, but it's a constant that doesn't really worry us so much. And so why don't I compare let's keep the 17 around and just do 17 over x squared. Right? It's the same idea. That denominator on the left is going to be bigger than the denominator on the right. And so I can compare with 17 over x squared. And then my question for you is going to be, is the integral from 1 to infinity of 17 over x squared convergent or not? And again, I think you have the evidence, the way to answer that. Think about what the integral of 1 over x squared would be, and whether multiplying that by 17 is going to change anything. Okay. So the very last example that I want to do is one where we use the comparison test in a different way. So I actually, and I intend for us to get more practice and go more in depth with this in the future. So, but I do want to do a little bit now. So maybe I'll go back to green. So I look at this, and if I think about what's going on, I think the numerator is always between 6 and 8. Right, because sine of x could be 1, it could be negative 1. And so that numerator is just going to be fluctuating between 6 and 8. And the denominator is basically the square root of x. Right, imagine x is like 1,000,000. Subtracting 0.7 from it is not going to really change the value very much. And so my idea is that this integral is basically like some constant, maybe like 6 or 8 or 7, divided by square root of x. And I'm going to do that integral from 1 to infinity. And this is actually going to be divergent. Right? Because it's basically like 1 over x to the p, where p equals 1/2. So that convergence test where you had an exponent required that that exponent be greater than 1 for it to be convergent. Right? So you can go back and review that that test if you like, but basically this is all really, really good evidence that kind of leads me to believe that our integral, and I'll write this down, I bet our integral diverges. Okay. And so let's try that with a comparison. So let's try let's see if we can compare. Can I compare? I want to show it diverges, so I need to show it's bigger. I need to show it's bigger than something that's divergent. Right? I want to show, if I want to show that this thing kind of goes off to infinity with area, then I need to show it's bigger than something that's divergent. And so I think about it and I say, well, I surely wish that that square root was just square root of x. And if I think about it and say, oh, well, actually, the denominator here is going to be, let's see, the square root, I subtract x minus square root of 7. Oh, this is going to be a smaller number than just the square root of x. So over here, I'm going to have a smaller denominator. So that's going to help me get a bigger fraction. And what about the numerator? Well, I haven't filled in the numerator on the right yet, but I probably want a bigger numerator if I want this inequality to be true. Remember, I want the thing on the right, I want to fill it in so that this thing on the left is going to be bigger. And so I look at my ingredients. I want a smaller denominator, a bigger numerator. And so I say, well, if I want a bigger numerator, why don't I just put 1 here? Right? Certainly 7 plus sine of x has to be greater than or equal to 1. And so now I look at it and I say, oh, well, now I have the square root of 1 over x. That's exactly what we kind of saw earlier. And so this does give a divergent integral. Right? So there's a lot in this video. You may want to watch this a couple times, and mainly what I want you to think about is just how we've simplified things with comparison, whether you believe the inequalities in terms of what's bigger, what's smaller, and things like that. So thank you for watching. Have a great night. Bye.